Hello students. Hello students. Please join the link. If you are getting my voice, just drop a message. Right. So the title is clear. I hope you got it. We are going to discuss the concept of Doppler effect. Yeah. So this is the last concept we have left over for this weekend part. Just a second, guys. Yes, students. Sorry for the delay. Right. So, Doppler effect. Already we have discussed briefly what is this Doppler effect. So this let me check once. One second, guys. Let me check whether the live has started. Yes. Waiting still. Streaming. Yeah. Right. Yeah. This is still showing waiting. Okay, then you guys, if you are getting my voice, just you can drop a message in the live chat. So, Doppler effect. So already in one of the sections we have discussed briefly what is Doppler effect and few of the cases of this Doppler effect. Let me once again explain this briefly for the other section students as they have not um, we have not discussed it in the other section. So Doppler effect. Doppler effect is nothing but the apparent frequency heard by an observer due to relative motion between source and observer. This effect is called as Doppler effect. This effect is called as Doppler effect. Still, it is not. Welcome to the physics session. Moving charges and magnetism. Now, this our class is based on. Yeah, now today we are discussing the last concept of this weekend portion from the chapter moving charges and magnetism, and specifically uh, uh, on the topic what is that moving coil galvanometer. Yeah, moving coil galvanometer. So let me give a minute for others to join. So still the people are joining. So we are going to discuss briefly about. Already I have informed you to go through the conceptual part. So we will see briefly what is moving coil galvanometer and some mathematical conditions related to moving coil galvanometer and few terminology like what is current sensitivity, what is voltage sensitivity, etc. and some factors which affects right which affects these, and then we'll discuss about how to convert a moving coil galvanometer into ammeter and voltmeter and what kind of questions will come based on this. We'll work out some examples as well, right? Okay guys, let us just start now. Okay, let us start now. So moving coil galvanometer. What is moving coil galvanometer? It is moving coil galvanometer. We know what is galvanometer. Already I have discussed, and it is, but it is different kinds of galvanometers will be there. Okay, but overall galvanometer is a device. What is a galvanometer? Is a device which is used for what purpose? For detecting current and also to measure current, very very low currents you can say. So it is called as a sensitive device. We use ammeter also to measure currents and galvanometer also, but galvanometer is a very sensitive device. That's why in the laboratory experiments, while doing experiments in the lab, you guys have to be very careful while dealing with the galvanometers. Okay, it is a very sensitive device. Okay, those I'm not just anyway. You guys may not make work more with the experiments. If any 11 students are following this, you have to remember this. Okay. Um, yeah. So what is moving coil galvanometer? moving coil galvanometer is a device which is used to measure device which is used to measure used to measure currents, small currents, you can say small currents, small currents, okay, and to which is used to and detect measure and detect small currents is called moving coil galvanometer. Okay, but it works. I sometimes you may get some conceptual based questions also in exams. The principle on which the moving coil galvanometer works is based on some options will be given. What principle? So you need to have an idea about. So usually, I will give you of moving galvanometer. What it consists of moving coil galvanometer. Why it is named as moving coil is in cost per branch, and we'll use a soft iron core here, of course. Okay, on this wire will be wounded, and when a current is passed through it, okay, because of the magnetic field, some force will be exerted on it, and that will create a couple, and that couple we call it as torque. So slightly it will be twisted, okay, and the torque acting on, if it is twisted slightly, the torque which is trying to rotate it will be called as a restoring torque. When it is twisted, it will be the torque which it tries to bring it back over the original position is called the restoring torque. It is directly proportional to the angle of twist. So this can be also expressed as torque is equal to some proportional to constant we call as a C into theta. C into theta, where C is a proportionality constant, we call it as a couple per unit twist. C is a proportionality constant, we call it as couple per unit twist. Whereas on this coil, this is having n number of turns, and if current I is passing through this, of course, provided a area of this loop is A, then, and if it is in this magnetic field produced by this, then a torque tau acts on this is given by n into b I b I a. Already we have discussed this derivation of this. You should have remember this. Okay, n I a b also can express, right? In vector form means n I into B cross A will consider in that way. If you want to say NIBA, right? So this is the torque acting on it. It is the maximum torque when theta equal to 0. It is nothing but angle between the magnetic field and area vector is 90. Then the maximum torque action it is equal to NIBA or NBIA. Yes, this both of these two are torques. If you equate them, you will get C theta is equal to NIB a, or from this you can write depending on while doing the numericals you may you will be given few data and will ask you to calculate few parameters depending on this relation. In this relation itself you can rewrite in different forms. So for this in this you can write theta is equal to NBA by C into I, you can write. That means if this entire thing is constant, then you can say theta is proportional to I. That means this gives the deflection in galvanometer. Deflection in galvanometer is directly proportional to current passing through the wire. You can also say this follows a linear relationship. The deflection theta follows a linear relationship with the what is that current passing through the wire. Okay, right. And here just you also just have to keep in mind that sometimes C, if you are asked to find C, what you call it is couple per unit twist. It's actually couple per unit twist. If that means for theta equal to 1, the couple is equal to C. So you can call it as couple is torque. So you can call it as couple per unit twist is we call it as C. So from this you can also express C is equal to this implies C is equal to C. This I can say equation 1. From this you can write this one. Otherwise, C is equal to NBA by theta into I, right? Or you can consider here, if you what you call, so if you write I is equal to, instead of this, if you write it as, if you write I is equal to from this, so equation 1 can be expressed this way or can be expressed this way also. I is equal to C by NBA or BAN. This arrangement you can write in different ways. Okay, BAN ban, C by BAN into what? Theta. From this you can also say I is directly proportional to theta. Theta is directly proportional to I, and I is also directly proportional to theta, I can mention. Right? So this is called, this term can be called as galvanometer constant. So this you can write I is equal to some constant k into theta. So that follows a linear relationship in this way. Also you can express that. Where this k is called galvanometer constant or figure of merit, where k, which is nothing but C by BAN, is called galvanometer constant. Galvanometer constant, which is also called as figure of merit. Figure of merit. Right? So it is equal to C by BAN. Right? This is briefly about recall. Figure of merit. And here we come across a few terminology like what you call current sensitivity, voltage sensitivity, etc. We'll see one by one briefly. What is current sensitivity of a galvanometer? Moving coil galvanometer. Current sensitivity. What is current sensitivity? Current sensitivity also denoted. You can use different symbols. Okay, sensitivity, if you are using symbol S, for representing current sensitivity, we use the symbol SI. Voltage sensitivity also, one more time will come across, that time we'll represent the, we'll use the symbol SV, voltage sensitivity, current sensitivity, like that. Current sensitivity is defined as, for a galvanometer, is defined as the deflection produced per unit current, or deflection per unit current. Here we have got the relation between I and theta, right? Deflection per unit current. So this I and I, deflection per unit current, will be called as current sensitivity. How to express this mathematically in this itself? Deflection per unit current. So what it gives? Deflection per unit current. If you bring it here, then we will get theta by I is equal to BAN by C, right? From this relation, that will be called as current sensitivity. So we can express here mathematically as, we can just, you guys have remember. I hope you remember the statement of it. If you want, you can, if you want, you can write down the definition form of this. What is current sensitivity? How to define it? How can you define this? Deflection per unit current. Deflection per unit current is called current sensitivity. Simply, deflection per unit current is current sensitivity. It is given by, S, that deflection per unit current, which you can write it as d theta by di, or simply you can write it as theta by I, is equal to, from the above equation you can write it as ABN or BAN by C. BAN by C is the mathematical expression for current sensitivity. While working out numericals, if you are asked to find this, with other parameters will be given. Based on this, if this is given and if other parameter is asked to given, if other parameter is asked to calculate, you have to use this carefully with all parameters to be in a particular system of units. Next point is, here corresponding to this is voltage sensitivity for a galvanometer. What is voltage sensitivity tells about? Voltage sensitivity of galvanometer is represented as SV, S suffix V, and just like current sensitivity is defined as the deflection per unit current. That means if you increase unit current, how much deflection will increase or decrease accordingly, we call as current sensitivity. So the same way, voltage sensitivity can be defined as deflection produced in the galvanometer per unit voltage applied. Per unit voltage will be called as voltage sensitivity. So it will be defined as what? Deflection per unit voltage. Deflection per unit voltage. Deflection per unit voltage is called as voltage sensitivity of a galvanometer. So it is mathematically again it is given as SV is equal to the same way you can write it as d theta by d v here, or theta by v. Simply you can write it as d theta by dv or theta by v, and this can be expressed as from the above expression theta by v. If you know, if you want how to find out, here we have, if you observe this equation, so there is no term called voltage, right? So but you have current. How can you express this current in terms of voltage? Is you know already from Ohm's law, V is equal to IR, or I is equal to V by R. So for whatever voltage sensitivity for a galvanometer is having some resistance. If you consider, if galvanometer is having some resistance, G is equal to, if G is equal to galvanometer resistance of galvanometer. Right, the galvanometer is voltage potential difference across this is nothing but, or in this if you write it as I is equal to is equal to V by R, and V is equal to IR. I what? Where R resistance of galvanometer is nothing but G. I into G if you take, then you can express what is this? Theta from this, from the above expression, theta as it is, you can also take it as, or here it is a theta by V, as V is this, you write V as I theta, Ig, but we know already this cannot, voltage sensitivity can be denoted as theta by I by G also. Theta by I is nothing but current sensitivity, so you can also write it as current sensitivity by G, current sensitivity by galvanometer resistance. Voltage sensitivity is equal to current sensitivity by G also. But current sensitivity is nothing but VAN by C. So from this you can write VAN by C into G. This is the this is how we can express voltage sensitivity in different other terms. Current sensitivity and hence voltage sensitivity. These are interrelated also, I can say. Right, here we have to keep in mind that, as what is G here? Galvanometer resistance. And this, you can say, we can change this, either current sensitivity or voltage sensitivity, by varying any of these parameters, any of these parameters, B, A, N, C, similarly here B, A, N, C, G, etc. How? Those by increasing those which are directly proportional, and by decreasing those which are inversely proportional. You can change the current sensitivity and voltage sensitivity of a galvanometer. Okay, but as we know, galvanometer, galvanometer will be used to measure or detect very small currents of the order of nanoamps or minus 10 power minus 9 amps. Okay, it is used. You have to remember that galvanometer, approximately you can say galvanometer is used to detect or to measure currents of the order of nano ampere, you can say of 10 power minus 9 ampere or nano ampere, you can say. Okay, now with the help of these terms we have to understand. Just we are not going into the detailed theory discussion of how the galvanometer construction looks like and working looks like, etc. So basic, I mean the important parameters we will see. So what is galvanometer and what is the principle on which it works on? It works on the principle of what you call a deflection of a coil in the galvanometer when the current passes through it, so that theta and I are linearly proportional. Right. So another thing is this, it will have some parameters like it will works based on this variation of these parameters, current and what do you call it, deflection, voltage and deflection variations that will be understood with the help of the terms called voltage sensitivity and current sensitivity, right? And here we come across a relation called shunt in case of galvanometer, and conversion of this galvanometer into ammeter and voltmeter. Before getting into the concept of conversion, we need to have an idea about what is a shunt. Shunt is nothing but a parallel resistance, a small resistance connected in parallel to any device, into anything is called as shunt. To another resistor or to a device, to ammeter, voltmeter, any device is called a shunt. Shunt is a small resistance connected in parallel to something is called shunt. Here we are going to connect to a galvanometer. That is the difference. Okay. So note down first in general what is shunt. What is shunt or shunt resistance, also we can call it shunt. The low resistance connected in parallel to, right down. If you guys want, you can note down this definition as well. Right? Just you can if you want, if you can remember, you can limit the low resistance, a low resistance connected connected in parallel to, in this case, galvanometer, connected in parallel to galvanometer. Why it is supposed to connect to parallel to galvanometer is just to protect it. Galvanometer is called shunt. It's called shunt. More clearly, if you want, you can write down a small resistance or low resistance connected in parallel to galvanometer to protect it from large currents, etc. is called as a shunt. Okay. And why it is supposed to be connected in parallel and what is the use of this? Usually it is used to give large ranges. As we said, the galvanometer gives small range currents. So to measure large currents, we used to connect this. We used to use shunt resistance, but it will decreases the sensitivity. The advantage is that, disadvantage is also there. Advantage is that it can regress the range of the currents so that you can measure larger currents, but at the same time it sensitivity decreases. So that is briefly about this. So to understand this, let us see the circuit representation of this. So if you, for example, if you have a galvanometer with a galvanometer resistance G is G galvanometer, and if you connect this to a small resistance in parallel, this is called as a shunt resistance. You can express it as S. Some books will give you RS, small resistance or shunt resistance, like that. Now this entire if a current, this is entire thing is connected to some source, so that current I is passing here. This current divides into current through galvanometer as Ig, and this as I minus Ig. If you take our current shunt resistance is this, and these two will again combine here and passes through to make the circuit be closed. If you mark these 2 points as A, B or PQ, something like this, then what you can understand from the Kirchhoff's current law is this: current approaching the junction is equal to currents sum of the currents leaving the junction. So I equal to Ig plus Is, right? I is equal to Ig plus Is, but I is equal to V by R. V by R. So you can also just say that if you want to know the equivalent resistance of this network, we'll use different ways of representing this. So you have to get what is I, then we have to find out equal potential across this device. See here, briefly, by making use of Kirchhoff's current law, we can say R equivalent, because this galvanometer and shunt resistance are connected in parallel. R equivalent is equal to parallel combination of R and S. So you can say sorry, G and S, G parallel S, or you can say 1 by R equivalent equal to 1 by G plus 1 by S. And simplifying this, you can say GS by G plus S, GS by G plus S. This is the R equivalent of this combination. If this is the resistance, then we can say the potential across the galvanometer or shunt is given by potential potential difference across galvanometer, potential difference across galvanometer is V G, or simply you can say V equal to as Ig into V is equal to IR. So here Ig into G you can take it as Ig into G, but Ig separately have to find out here. Otherwise, we have to just what do you call it? Simplify Ig from the above expression, and you have to substitute here. From this, Ig is equal to I minus Is, where Is is current through this. I is equal to V by R. V will be common. Okay, so V by R. So from this, you can simplify, and you can write it as you can also write it as V is equal to I into R equivalent. V is equal to I into R equivalent. It is equal to I into Gs by G plus S. So different ways you can express this. This is one of the way you can express. So here as what you have understood is galvanometer and shunt resistance, they are connected in parallel, and hence the potential difference across galvanometer and potential difference across the shunt resistance are equal, that is equal to V. So you can also write what is this V across P and Q is equal to I into Ig into G or Is into S. This is also just to make use while working on the methods. There's some short relations. The next point is how to convert a moving coil galvanometer into voltmeter and ammeter. We'll see briefly, then we'll try to work out some questions. We'll try to work out some questions. Right. So if I write down next is conversion of galvanometer into ammeter, or moving coil galvanometer, moving coil galvanometer, or simply galvanometer, conversion of galvanometer into ammeter, conversion of galvanometer into ammeter. So how to convert galvanometer into ammeter? The simple condition you have to remember is why the ammeter is used for. Ammeter is used for measuring currents. You have to remember that for measuring currents, the currents measuring device has to be connected across that element. Say for example, if you have a circuit in this, there is a resistor. If you want to measure the current through this, you have to connect ammeter in series with that. So ammeter always has to be connected in series with the element through which you want to find the current. Whereas voltmeter, voltmeter to measure voltage, you have to connect the voltmeter in parallel to the device across which you are supposed to find out the potential difference or voltage. So now let's come back to this ammeter. So you should know what is ammeter. Ammeter is a device which is used to measure current. Right. So now for converting galvanometer to ammeter, you have to just keep in mind that you have to connect a small resistance or shunt resistance in parallel to the galvanometer. So note down this. You may get some direct concept-based questions also based on these points. But to convert galvanometer into ammeter, options will be given. A shunt resistance will be connected in series with a galvanometer, or a high resistance should be connected in series with the galvanometer, or shunt resistance will be connected in parallel with galvanometer. Right, both 1 and 2, something like that. Options may come. So you should have the basic idea about the conceptual point. The I can write it as a definition point of it. So what is this? Is it you can say to convert galvanometer galvanometer into ammeter we have to have to connect a small resistance or shunt resistance, let's say small resistance in parallel with galvanometer. In parallel. The circuit, I will give you a small circuit diagram to understand this. So if you have, this is a galvanometer with a galvanometer resistance G, and you should connect a small resistance or a shunt resistance in parallel to this. So this is called a shunt resistance. Yes. So if a current I passes here, I, so this will divide into Ig and Is, or I minus Ig you can call as Is. So this will together, what is that? Galvanometer together with a small resistance in parallel will be termed as ammeter. This will be termed as ammeter. So mathematically you can say the resistance that with the small resistance that should be connected in parallel to this to convert this into ammeter is nothing but this is how much that value should be depending on the range of current to be measured. We have to calculate sometime. The question should be asked based on this. So to understand this, we have to just say, as you have to just keep in mind that potential across both will be same. So from this you can say potential across shunt resistance is equal to potential across galvanometer. So potential across shunt resistance is V is equal to IR. So IS into resistance of this is S, and potential across galvanometer is IG into galvanometer resistance G. Right. From this we can say what is that? S is equal to shunt resistance. S is equal to uh, Ig into G by Is. But resistance is equation 1. But from the circuit itself, you can say I is equal to what? Ig plus Is. Here you guys see I is coming and dividing into Ig and Is. So Ig plus Is together is I. So from this, can we say Is 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 equal to I minus Ig? I minus Ig. From this implies Is is equal to I minus Ig. So if you substitute this here, then like if you this is given directly, you can take it as. Otherwise, sometimes we get one of the simple term called range. In such cases, you have to use one simple relation. For that purpose, I'm giving you this. So S is equal to shunt resistance is equal to Ig into capital G by, you can write it as I minus Ig. I minus Ig. Here, this Ig, if you bring it here, or if you take the Ig's out here common, then this Ig can be cancelled. Anyway, you can write. So in this case, in that form, you can write G by I by Ig minus 1. You can write this ratio. Actually, this is usually this relation usually we use to calculate some resistance related formula. Here we will take the ratio of I by Iga as n. That means to increase the range by n times, or to what you know actually this the current sensitivity and the deflections will changes actually the interrelated. So here you can say if you are increasing the current means the sensitivity should decreases. Always you have to keep that in mind. So here, so if you are increasing the current by n times means the sensitivity should decrease by n times. In that range, here you can say that I by Ig will be called as range of the current. If you consider I by Ig is equal to n, is nothing but a range of current to be increased or decreased, right? Then you can consider this as S is equal to G by n minus 1. G by n minus 1. Yeah, that while doing the numericals directly, this relation also will make use sometimes. Here, what is n? We said I by Ig. This can also be expressed as, n is equal to I by Ig, or you can write it as the old value by new value. You can also say that one. This is old value by new value, or uh, new range by old range. The terminology while dealing with the numericals we can understand in different ways, right? This is a simple way of converting what you call galvanometer into meter, and this formula you have to use while working on the numericals. The next simple concept here we have to just have an idea about is voltmeter. Let's see quickly what is voltmeter and how to convert voltmeter galvanometer into voltmeter. Then we'll do some numericals. Voltmeter. Voltmeter. or conversion of galvanometer into voltmeter. That is right. Conversion of galvanometer into voltmeter. Conversion of galvanometer galvanometer into voltmeter. Into voltmeter. So for converting galvanometer into voltmeter, you have to connect high resistance in series with the galvanometer. What does that mean is, you have to just here I would like to give one more few points, 3 points actually, maybe while doing the questions also I can give. You have to remember that ammeter is used to measure currents, means why you have to connect the small resistance in the parallel with this while calculating current is, no, the device while measuring current, the device which you are using to measure current consume any current, shouldn't consume any current. That's why you should connect. I mean, it shouldn't consume any voltage. That means the entire current should pass through. Shouldn't consume. It doesn't mean that it shouldn't consume any current. Shouldn't consume any potential. No potential should across this. Entire current that is coming should pass through. So if that is possible only when it is having least possible value. So we can say the ideal ammeter will have zero resistance. We say ideal ammeter ammeter will have zero resistance units. Whereas ideal voltmeter will have infinite resistance. So that means no current should pass through the voltmeter. That's why then only it will give the correct value or accurate value. So that's why it is used to measure the potential differences more accurately than voltmeter. Normally speaking, the galvanometer, that is we have already discussed that potentiometer. The difference between potentiometer and voltmeter, etc. So this serves the purpose of measurement of potential only. But with this condition, what is this? How to convert galvanometer into voltmeter? To convert galvanometer galvanometer into voltmeter. What you have to do? We have to connect a high resistance. We have to connect a high resistance in series with galvanometer. In series with galvanometer. In series with galvanometer. So pictorially to represent that, let us see here. There is a galvanometer. This is a galvanometer having galvanometer resistance. Then you have to connect a high resistance, high resistance R, high resistance R. Then this combination will be called as what? Voltmeter. This together will be called galvanometer together with high resistance will be called as voltmeter. Whereas galvanometer together with a small resistance connected in parallel is called as ammeter, whereas galvanometer together with high resistance in series is called as voltmeter. Will serve the purpose of voltmeter. Now, if you say if a current I is passing here, the same current passes through galvanometer and also through this resistor, it will come out. If you consider this is point P and this is point Q or A, this is point A or this is point B or whatever it is, PQ or AB, then potential drop across this will be equal to potential drop across the galvanometer plus potential drop across the resistor. Okay, this you have to just keep in mind. This potential drop, if you connect this to a battery, that if this is the total potential drop, it will be equal to potential drop across this plus potential drop across this. That means you can also say if total potential supplied is V is equal to potential drop across the galvanometer plus potential drop across the high resistance. You can also write it as V is equal to IR. So that is current through the galvanometer into galvanometer resistance plus current through the resistor, that also same only, actually Ig only will pass through that, so you can say Ig into R. So we can say V is equal to Ig into what? G plus R. Or by making the use of this relation you can also calculate the high resistance required to convert the galvanometer into what you call voltmeter also. To find that you have to say V minus IgG by Ig, you give you R. So depending on the given data, you have to use the different relations here. So from this you can also say, you can say this is 1 and this is 2. Hmm? From 2 you can say the high resistance required to convert galvanometer into um, voltmeter in terms of galvanometer resistances R is equal to, so this is IGR is equal to V minus V minus IGG, right? V minus IG into capital G. So IGR is equal. So therefore I resistance R is equal to this IG, if it comes here VG by V by, you can say V by IG minus IG as you cancel, minus G you get. So you get V by IG, V by Ig minus G will be the value of I resistance required to convert galvanometer into voltmeter, right? So here also you can come across one simple relation, that is simply if you want to say that the resistance needed to connect resistance needed to connect in series with the galvanometer should be R is equal to, if you want to say already as you know, N is equal to what? N is equal to I by Ij, right? In terms of this, if you want to just express this, you can write in a different way. So that is in terms of currents, but here if you want to just express the same way here in case of voltages, if you take N is equal to new range by old range. If you take new range, what does it mean of meaning of new range and old range? We can understand when doing the numericals. We'll see quickly few numericals as well. New range by old range, new range voltage by voltage, let us say V2 and V1. So this V2 can be taken as V is equal to current, potential difference across the galvanometer plus resistance, can be expressed as Ig into G plus R by, the old one is nothing but only galvanometer is there, then Ig into G, then it gives 1 plus R by G, it will gives. This will be taken as N in this case, whereas in case of here in terms of resistance, in case of ammeter conversion, N is equal to I by Ig. These relations you have just to keep in mind. So now let us see how can we go through few questions. First in level 1 exercise 1, level 1 exercise 1. That is 7, level 1 exercise 1, level 1 exercise 1. Mm, the question is question number 47. Question number 47. A galvanometer has a resistance of, galvanometer resistance is denoted by G. Galvanometer has a resistance of G is equal to 400 ohm. The value of shunt, so that its sensitivity is to be reduced by uh, 1 by 50 times. Its sensitivity is reduced by 1 by 50 times. Sensitivity means the range, right? So you know, what should be S, so that its sensitivity will be reduced by 1 by 50 times. So then what relation you have, you know, for calculating what you call shunt resistance, shunt what is the value sensitivity to be reduced by much 1 by 50 times. So 1 by 50 times, you can say it as 1 by 50 times. So let us see whether how can you take this one. So as S is equal to shunt resistance, just you have to remember that in case of this conversion of galvanometer into ammeter, S is equal to what? Yeah, G by I by Ig minus 1 or G by N minus 1, right? S is equal to G by I by Ig minus 1. Here I and Ig, if you observe, always I will be divided into Ig and I, so I will be greater than Ig always. It will be larger and this will be smaller. You have to remember that is equal to G by N minus 1 as we can take. So to reduce the sensitivity by 150 times means what you get if you substitute this here you can take the ratio of what do you call it? The sensitivity of galvanometer means the total current by current of galvanometer is can be considered this as its sensitivity. So 1 by 50 times. If you take it as 1 by 50, then if you substitute and find out what do you get? Is with G is 400 by 1 by 50 minus 1. It reduces by. So we can consider the negative sign represents a decrease in value. 1 by 50 minus 1. It reduces by 1 by 50, right? So can you take it as it is reduced by 1 by 50, not reduced to. So mm, N is take it as reduces by 1 reduces by 1 by 50 times means in total 50 times you can take it as 50 minus 1 that I will take this one as sorry yes guys here not n I have to take this value the uh, the sensitivity means I by Ig if it is reducing by 1 by 50 times means 1 out of 50 times. So then you can consider this is 50 times it reduces means 50 will approximately is 40 by so 400 by 49 400 by 9 approximately will be equal to 8.16. Here we'll get it as 8.16 ohm will get. This is the resistance of shunt value, small resistance value. If it is less than is not equal is not approximately equal to 9, there is what we call 6.16, 7.16, 8.16 and 9.16, and then you have to just do this kind of questions little carefully also. So this kind of values are given by this. So next one more simple question this I would like to give you guys here is few related questions how to deal with this. Let us see. Next in level 2 exercise 1, level 2 exercise 1 we'll see question number 61. In a galvanometer, if 5% in a galvanometer, 5% of the total current in the circuit passes through it. If the resistance of the galvanometer is G, then the shunt resistance S connected to the galvanometer should be. So let us consider the given data here. What is given here is in a galvanometer, so 5% of total current in the circuit passes through it. Let us say this is a galvanometer. 5% of total current. 5% of total current. If total current is I passes through the galvanometer, so I is equal to that means this is nothing but Ig. Ig is equal to 5% of total current is Ig passes through the galvanometer, and if the resistance of galvanometer is G and the shunt resistance is yes, then what should be the value of shunt resistance in terms of G is the question. If 50%, 5% of the total current is passing through the galvanometer. This is I, there is Ig, Is. So what you have to just consider here is, what you have to consider here is, um, to find what should be S value in terms of G is the question. To find, you know already S is nothing but what? G by I by Ig minus 1, or G by n minus 1. Here actually I and Ig relation is given. Directly I can use it. So no need to use the term n. So G by I by Ig. If you bring this Ig here, it becomes 100 by 5. So from this you can say I by Ig is equal to 100 by 5. So 1 5 2 0 5 20 is right. So it will be 20 minus 1 is equal to G by 19. So the you can say the value of S will be in terms of G is G by 19. S is equal to G by 19. G by 19. Right. This is how you have to work out this kind of questions. Right. Let us see one more such question. One more simple question. In level 2 exercise 2, let's see question number 35. Question number 35. If you relate to questions, you'll see. It is given that a galvanometer required 10 microamps for one division of its scale. It is to be used to measure a current of 1 ampere to full scale deflection. The scale has 100 divisions. Then the value of shunt, if the resistance of the galvanometer is 999 ohm, is right. How to work out this kind of questions? How to work out this kind of questions? What is this given? What is given here? A galvanometer required 10 microamp for one division of its scale. For one division, 10 microamps it requires. So what is this galvanometer requires? Means Ig is equal to 10 microamps for one division. It is to be used to measure a current of 1 ampere to measure a current of 1 ampere. It is to be used to measure a current of 1 ampere to the full scale deflection. Full scale deflection means total current should be 1 to measure a full scale deflection 1 ampere means if the total current to be 1 ampere. The scale has 100 divisions. The total number of divisions is number of divisions is equal to 100. So for one division it is having 10 microamps. For 100 divisions, Ig will be equal to how much? Ig is equal to 100 into 10 is equal to 1000 microamps. Then the value of shunt, what should be the value of shunt provided? The galvanometer is having a resistance of G is equal to 399 ohm is the question. So simple relationship you have the relation between the shunt resistance and galvanometer resistance is shunt resistance is equal to galvanometer resistance by I by Ig minus 1. I by Ig minus 1. You know, here in this case, for the full scale deflection of 1 ampere means for the total current to be 1 ampere with the galvanometer resistance of 399 ohm, full scale deflection current I is 1 ampere means I is 1 ampere. Ig will be equal to what? 1000 you can say it as yeah, this is 1 second. Yeah. For the scale is having 100 divisions. So yeah, so the total current should be 1000 minus not this one. The number of divisions, the range we have to take here. If you take this as in terms of n minus 1, as n is equal to I by Ig, right? For a scale of yeah, for a full scale of 100 divisions, it is having 1 ampere means the current in the one division of for a one division scale current is 10 microamps, then the total n value will be taken as I by Ig is equal to 1000 is a 100 into each scale is having each division is having 10 microamps, so 1000 you can take it as 1000 microamps the current is, otherwise then in terms of the range you can take it as 1000. So if you take this way, then you can take S is equal to 9999 by 1000 minus 1, which is equal to what is this, triple nine by triple nine by triple nine, so it is equal to 1, right? It is equal to 1. So you can say the shunt resistance, that is the small resistance to be connected, S should be equal to 1 ohm. The shunt resistance or small resistance to be connected should be 1 ohm, right? So that is how just we have consider this kind of questions. These are few ways of doing this questions based on conversion of ammeter to voltmeter. So consider this appropriately, and try to work out few more similar kind of questions. So this is briefly about what you call moving coil galvanometer and this conversion to ammeter and voltmeter. You guys practice few more questions. If you have any doubts, you can drop me a message. Okay. So I'm winding now. I'm winding the session now here. Okay, you guys go through and prepare, revise.